In this video, we're going to continue to explore our measures of dispersion. We're going to explore two new measures of dispersion today as we look to tie our measures of central tendency and measures of dispersion together. At this point, we've already examined the mean, median, and mode as our measures of central tendency, and we've looked at things like the range, interquartile range, quartiles in general as our measures of spread. We'll begin this lesson by looking at a statistic known as the deviation of a data set. A number of the other statistical measures we looked at, there was sort of one calculation for a data set. The deviation's different. There is a unique deviation for each value in your data set. The deviation for a data value is calculated by taking the data value itself and subtracting the mean. The result of this calculation gives us a number that has two important characteristics to it. First of all, the magnitude or size of that number is a measure of how far away a data value is from the mean. The sign on the number, whether it's positive or negative, indicates where that value is relative to the mean. Your deviation is going to be positive if the number is bigger than the mean, and it's going to be negative if your number is smaller than the mean. Being able to calculate individual deviations is good, but it stands to reason that if we were to have a mean of those deviations or an average of the deviations, that would be a really effective measure of dispersion. It would tell us on average how far the data is spread out away from the mean. To illustrate how that works, I'm going to take this general data set of 6 values and determine the average of the deviations. So here you can see I've set up the equation to calculate the mean of my deviation values. They're all added together along the top, and because there are 6 of them, I'm dividing by 6. Given that everything on the numerator is joined by addition, I can drop the brackets and start to group some terms together. I'm going to take all the individual data values added together and move them to the front. And what I notice is I'm subtracting the mean 6 times, one for each deviation, so I'm going to simplify that in the numerator by taking away 6 times the mean. Next, it seems to me like the best bet is to split up my fraction and take all of the data values that I have added together and divide them by 6, and then have the minus 6 times the mean be divided by 6 on its own. This is actually going to simplify in a really nice way in our next step. You see, the fraction on the left is just equal to x bar. That's the calculation for our mean. We're just adding the data values together and dividing by 6. The fraction on the right has a 6 in the numerator and the denominator, so I can actually reduce that out and just leave behind x bar. Unfortunately, this leaves me with a weird conclusion. I end up with the mean minus the mean, and this just simplifies to 0. It's really important to note here that this isn't a special case that caused this to happen. I'm using only general values in this derivation, so this seems to suggest that no matter how large the data set happens to be, nor what those values happen to be, the mean of the deviations, if I go to calculate it, is always going to work out to be 0. If you think on this for a moment, the conclusion we just came up with shouldn't seem too outlandish. When we determine the mean in the first place, we're taking a wide variety of values and condensing them towards a central value, which is the mean. So it stands to reason when we go to look at the deviations, we're going to have some deviations that are positive because they go above the mean, and then we're going to have negative deviations for the values that were below the mean. And realistically, we're going to have sort of an even distribution on either side of the mean for those values. And then when we go to add them back together, it kind of makes sense that it's going to just resolve down to 0 because we've already accounted for condensing away those differences when we found the mean in the first place. So what does this mean for us then? Does this mean that we can't actually average out the deviations? It seems like that would be a very handy value to have, but mathematically just averaging the deviations isn't going to cut it. So one way mathematicians have resolved to fix that problem is by calculating something that's called the variance. Here, instead of just averaging out the deviations on their own, what we actually do is we square the deviations first and then average those values. The reason why this can be useful is because squaring the deviations eliminates the negative values. So now when you go to add them together, you don't actually have the positive deviations being canceled out by the negative deviations. Now this value of the variance isn't exactly the same thing as a mean of the deviations, but it is a helpful measure of spread. See, the larger the variance, the more spread out the data is from the mean. It also indicates that the data set is less consistent. However, if the variance was really small, it means all of our data values are closer to the mean, and it means it is more consistent. And we said in our last lesson, greater consistency gives us greater confidence in making predictions based on that data set. To get closer to estimating that fundamental idea of an average deviation, we square root the variance to determine what we call a standard deviation. So a standard deviation is a really good indicator of how spread out the data is around the mean, and it's a value we'll use not just in this unit, but in other applications as well. It is important to note the standard deviation is a non-resistant measure of dispersion. It can be skewed due to its dependence on the mean. Remember, those extreme values on the fringes of our data sets can skew the mean significantly, and they'll have a similar effect on the standard deviation. While this does not invalidate the use of this statistical measure, this is something that's good to just keep in mind as you do data analysis. To give you a sense of what standard deviation is useful for, we're going to look at a situation where we're looking at data for AA batteries that are being used in an emergency flashlight. So we have a person who's recorded the number of hours of continuous use that the batteries last before they need to be replaced. And this person has experimented with 2 different brands and so has collected data on both of those brands. If I'm going to calculate the standard deviation by hand, I'm going to want to do this in a table. It's just going to help to organize the data as we work through it. And so I've presented 2 tables here that I'll use for that purpose. Before I can calculate any of the deviations, I am going to need the mean. So I've done that calculation on my calculator and determined that the mean for brand A is 5.61 hours of battery life. Next, I've populated my second column with the deviation values. I took each value from my data set and subtracted the mean from it to get the values I've put into the second column. And now finally, I've completed the third column of the table by squaring all of the values that are in the second column of my table. So I've taken each deviation, squared it, and again, that's removing the sign, but preserving some element of the magnitude of that deviation. I'll need to average those values out, so I've written the sum of that column below in red as 10.9087. I will divide that by 7 as there are 7 values in my data set. If you're following along on your calculator, the value that you have now is not the standard deviation yet. What we've calculated so far is the variance. We need to square root this value to get the standard deviation. So by square rooting the variance, we get the standard deviation to be 1.25 hours. For brand B, I'm going to ask that you get your calculators out and attempt to follow along by calculating all the statistical measures we did for brand A in the same order. The mean battery life for brand B is 6.2 hours. Now I've written in the deviations. Notice how the deviation for 2 values is 0 because my mean is actually within my data set here. And now I've squared my deviations so I can add them together and average them out. If you've finished calculating the standard deviation correctly, you should get a standard deviation of 1.13 hours for brand B. Calculating these measures is very helpful, but now we want to formulate a conclusion based on the evidence that we've found here. Looking at these values, we can determine that brand B has a longer average battery life of 6.2 hours versus 5.61, and the standard deviation is smaller, indicating that these batteries are more consistent in their lifespan. As a customer purchasing batteries, these would be characteristics that are ideal if you're looking to purchase the best battery possible. You want batteries that will last a long time, and you want to know that the batteries will be consistently lasting a long time. Now the data we just looked at was ungrouped. If we had a larger sample, we would have a frequency table with grouped data or possibly continuous data. And so we want to look at how we would calculate the standard deviation there as well. Although the algebraic formula to do this is presented on your screen now, the complexity of the table that would be required to do this calculation is a little bit too inconvenient for our purposes. We need to be more efficient in our problem solving, and so we're going to turn to technology to help us speed up that process. Thankfully, this is a value we can already calculate because the standard deviation is presented to us by our calculator when we do one variable statistics. So in that summary report of helpful statistics, you'll see a value that says sigma x, and that's our standard deviation. You can see it here presented on both the TI-84 and the TI-Nspire. If you were looking to calculate standard deviation, you would enter your data for grouped or continuous data sets in the same way we've done before by using a frequency list if your data is presented in a frequency table, and using the midpoint of a class interval if the data is continuous. Then you'd calculate your one variable statistics as normal, and the standard deviation is among the values that's given to you with your mean and your measures of spread, like your quartiles, your median, your min, and your max. Some of you might notice that there's a value that's positioned directly above the standard deviation I'm referencing that's labeled as S rather than sigma. And if you look closely when you do your one variable statistics, you'll often notice that that value is very close to the sigma value that we're using. This is the distinction between a population standard deviation versus a sample standard deviation. The sigma value is an estimate for the population. S, or sometimes written S sub n, is the sample standard deviation. If a sample is sufficiently large, then that sample standard deviation S will provide a better estimate than sigma. However, for our purposes in this course, we will not be using S when we calculate standard deviation. While being knowledgeable about the differences is helpful, you will never actually have to use S, the sample standard deviation, in practice. To tackle our second learning goal for this lesson, you're actually going to be completing an investigation from your textbook. This will allow you to explore the impact of constant changes on a data set to determine how those changes will impact your measures of central tendency and measures of spread. Otherwise, standard deviation and variance round out our toolkit for one variable statistics that we'll be learning in this unit. And so now that we have a robust set of statistical measures that we can use to analyze a data set, we'll be able to dig a little bit deeper into data sets and come up with some valid conclusions about what's happening.